I have some important news. Important news coming up. Anyway, important news is that next week, Tom Barkley of Microsoft Research was supposed to be here, but he bailed. So I tried very hard to shuffle him around with other speakers, and nothing worked. So next week, unfortunately, there won't be any Colloquium. Some of you, of course, already are rejoicing. But the point I'm making is that those of you who are taking the course as a Colloquium CS390, you're still obligated to turn in the paper. You're not going to wiggle out of that. Okay, so therefore our next Colloquium meeting is October 9th with Julia Grace. Today I have the distinct pleasure and honor of introducing somebody who was at the very site of creation of relational databases. Knows all the secrets of Codd and Gray and all those other people. Please tell us all the important jokes. Bruce, Lindsay.
Thank you. Well, yeah, I'd like to discuss some pretty interesting stuff, because this is a technology that started off just somebody's idea, and not so long ago, 35, 40 years ago. So what have we got to? Let's start with where we are. Relational databases run the world. Sorry, they're big business. They're about $10 billion a year now. They use huge transaction loads. These are 10-year-old numbers. Double everything and multiply by 10. But you know, without them, there would be no such thing as credit cards. No such thing as identity theft. I mean, so lots of convincing this is important stuff. I mean, you could not probably get home today if the relational databases of the world stopped now. And what they've enabled businesses and organizations of all kinds, education, government, non-government organizations, is to extract value from the data they have. You can have all the data in the world, and if you can't get what's in there out of it, it's useless. You know, your iPod could be really full of all kind of music, but if you ain't got the headset, earphones ain't going to do you any good. So trying to get the value from the data is the real trick. And what relational databases enable is much more effective extracting information, useful information from the data to basically get your bill to you so you'll pay your credit card. In 1970, Ted Codd wrote the seminal paper, The Relational Model for Large Shared Data Banks. It ignited a fierce debate in the database community. In 1971, at Ann Arbor, Michigan, Ted Codd and Charlie Bachman were there. Charlie Bachman was the champion of navigational databases. Everything points to everything else. And they had a little debate, and yeah, fireworks, lightning bolts. They were really going at each other. Because Codicil and IMF, hierarchical database of the day, argued that implicit structure of one thing pointing directly to another thing captures meaning and gives good performance. But the relational data model argued that because the navigation world depends on application-managed relationships and collections of things, very limited, because unless you originally thought that this should be related to that and these things should be collected together, end of story, couldn't do anything else with that. Whereas the relational model dynamically creates relationships between things and dynamically defines collection of things based on predicates about those things. You could say the values of those things, but more generally it's a predicate. That this is related to that because they have the same color hair. Or this is related to that because shoe size is larger on this one than that one, and one is from Tanzania. So relationships are dynamically defined. And that's the key to exploiting real value. Because when an idea comes into your head that, gee, it'd be nice to know, you can define those relationships without having to take a bottle of good stuff to the database administrator and say, I would really like to have the database schema reorganized and changed so that I could ask my question. Because, you know, it takes a hell of a big bottle most of the time to get that accomplished. The real secret here was non-procedural query specification. Specify what it is you want, not how to get it. Because old databases will always specify how you get it in terms of the paths for getting things that were in those databases. So yes, you can get somebody by their name because we have an index on name. The relational model will say, go ahead and ask for a name. If we ain't got an index for a name, we'll figure out some other way to do it. Maybe not an efficient way, but we'll do it, damn it. So specify what is one, not how to do it independent of storage structures and access paths, pointers and indexes, levels of indirection. You know, computer science, all problems are usually solved by just simply an additional level of indirection. But getting kind of deep now, we've got a lot of levels of that. And the relational model allows defining data integrity independent of the application programs that manipulate the data. So you can say there's something about this data that that people should be under 12 feet tall. And the database itself, with this specification, can say, hey, you're trying to make this bird 13 foot tall. We don't allow that. Go away, come back later when you got a better idea. To validate and, secondly, reactive changes. Say a little bit about that if we don't completely run out of time. So why did the relational model win? And it has won. I mean, really, all databases are relational if they're databases at all. There's some things that call themselves spreadsheets pretending to be databases. Not quite. Ad hoc queries. The first and earliest prototypes of these systems allowed queries to be posed from an interactive terminal and then an answer to come back in moments. When the query wasn't too complicated. Sometimes hours. But we'll talk about that later if I get time for that too. So ad hoc, so it wasn't so much that the query was non-procedural. It didn't depend on the access paths and things like that. The fact that you could type it in and get back syntax error right away instead of putting in a deck of cards, waiting for them to restart the system and try out your new query, because you had to restart the system to try a new query in existing database systems. And put in some new DDL, or what do we call those cards? Those PD cards? It was terrible stuff. And so you could get right away, it would come back, syntax error for your query, or a goofy answer that doesn't seem right in the query. That wasn't really what I really wanted to ask. So instant feedback to generate reports and answers and figure things out, and online data definition. And you can define a new data set, a new table, create an index without bringing the system down. And again, all the systems were out there in those days, IMS and the codicial databases and IDMS. You had to basically stop the system, type some very serious mumbo-jumbo, and then you could maybe start it up and have the new stuff. So you had to stop all ongoing work. So online database, simplified development test, ACID transactions, a clear and convincing definition of what a transaction was, what the interaction between concurrent applications running against the same data might should be, concurrent applications without tiers, and finally, of course, I mentioned the non-procedural query language, which was developed called SQL. There was another language at that time from Berkeley called Quell, just about as good as SQL. I can't say that one's a whole hell of a lot better than the other. SQL's been accepted as the standard, and has in fact got some quite nice enhancements over the last 20, 25 years. Well, the early systems were slow. The turtle, whoops, what happened there? Back. The turtle. That was the logo of an English project at Berkeley. Because they were slow. They seemed slow compared to everything else. Of course, computers were slow in those days. In 1992, TPCC is a benchmark, well understood benchmark. It's been running for 25 years of online transaction processing performance. In 1992, Tandem computers announce 188,000 transactions a minute at a cost, excuse me, that's wrong, 1992 is 54 transactions at a cost of $188,000 per transaction. In 98, it was 52,000 transactions at $135 a transaction. I looked it up this morning. It was a little over 6 million. You know, a million. Much bigger. At a cost of $2.81. That's the record today. TPCD is a business intelligence analysis queries, finding averages and things like that over huge data sets. So that big change. Today's number, instead of 1,000, D became H. I'm sorry, they changed it about 20 years ago to be slightly different. 340,000, excuse me, at a cost of $32 per, instead of 500, over a 10 terabyte database. That was the 10 terabyte database. Of course, you know the CPU is now about 1,000 million instructions per minute, per second, and it's about a tenth of a cent per million instructions per second. Disk drives, what are they? A terabyte disk costs about $250 a SATA disk, terabyte. That would be about a hundredth of a cent per megabyte, I think. So hardware helped a lot, but there were many software innovations along the line to make it go faster. So let me see if I can go through a few. Oh, let's talk about transactions. I'll try to make this quick because I could make this a semester course if you like. This is probably the most important thing. What good? How did everybody say, well, we can make some money from our data. If we had the data, we could analyze it and learn good things and be more efficient and all that kind of stuff. But if you're going to get the data, it better be safe. If I'm going to have my bank account there, it better get it right. So this is what they got right. The things were reliable enough that you could trust the computer more than the paper. Because until you got rid of the paper, the cost of doing business transactions had a lot of extra friction. We call that transactional friction. All right, all or nothing. Multiple actions. Update this account, read that account, update this other account. Do it as though it happened atomically. Nothing in between. Very important. All or nothing. Despite failures at any moment, any time, most embarrassing moment, think of having a failure there. Can't lose any money. Can't have debited one account and credited another. Consistent, an application defined transforms a database from one consistent state to another consistent state. Consistency, of course, in the mind of the application domain, like all the accounts that are totaled up to the right amount all the time. Isolation. Concurrent applications run as though they were serially run one after another. That's concurrency without tears. Could you imagine if you had to write a program updating various things all over the database, and I could write another program updating all things all over the database, and we had to say what the answer was if there was no kind of synchronization between what we're doing? So, isolation, concurrent applications act like serial applications. You can't prove otherwise. And finally, durability. We mentioned that right up front. Committed changes survive failures. Failures of software, like the operating system kernel may say, I don't like it, doesn't smell good here. Stop. The hardware can stop between any two instructions. The disk could lose all of its contents at any time. And in fact, furthermore, the nasty thing that disk can do is if you're writing a block of 8K data, it can write 4K, shut itself off, or the power goes out and says, okay, and you return it back on. It gives no checksum errors. It says, here's your 8K, 4K old, 4K new. It doesn't work so good. Any kind of failure recover from local information up to, but not including fire, which wipes out the whole place, flood, and so I went to Berkeley in the 60s. We also have to include the possibility of losing all the data due to insurrection. Okay, this is the trick. Automaticity durability despite failures of any in-processor's disk communication software, write-head log protocol, write the log to the data change before writing the data, change data written before or after commit. Commit is written into the log. Redo committed transactions after a system restart from the log. Undo uncommitted changes from the log, using the log. And in a distributed system, where there are two systems, you know, they both got to agree whether they're going to commit to these changes. It's a hard problem. You know, you can't have one guy send a message to the other guy, attack at noon, at dawn. Well, should I attack at dawn? I sent the messenger. He would have had time to get there, but he might have been captured. And if I attack alone at dawn, I'll be doomed. The guy at the other end, the messenger comes and says, attack at dawn. How does he know I got the message? Will he really attack at dawn with me? Well, there's a thing called Twophase commit protocol. We can solve this almost, and there's some very nice, interesting protocols for consensus when the messengers get captured and everything. The Byzantine agreement protocols where the messengers can go bad, and generals can be turncoats. And also the consensus protocols when I sent a message to everybody to attack at dawn, and as long as 3 of us attack, that's good. Even if the 4th guy's already been wiped out, the agreement protocols. Very nice stuff, modern stuff. You've got to learn about it if you're going to know anything about distributed computing. Okay, relational innovations, cost-based query optimization. Many ways to execute a given query. Because if it says find all the bonds in the database, well, you can look at everything in the database and see if it's a bond. Or if you had an index of hair color, you can just look at them. Very much more quickly find the bonds. So there's lots of choices of access methods, indexing, scanning, index plus fetch. Indexes often don't have all the data. They point to more data that you go to. Sometimes it's much worth the while that if you've got a lot of hits out of the index, to take all the pointers to data and sort them so that some of the data things end up on the same page. So when you fetch them, you don't fetch the pages as much. There's different ways of doing joins between one data set and another. There's nested loop join, hash join, merge join, there's a bunch of others, but those are the main ones. With little variations of early out, star join. Lots of choices how to execute the query. Not all of them equally efficient. Matter of fact, there can be huge orders of magnitude in performance between a query, between different methods. One method may well finish the whole thing and get the right answer in a few seconds, and another method may take a few days. So, how do you deal with this? Well, you estimate the cost of the alternative plans using the table and record sizes. So we keep track of the data. We compute statistics on it. How many records are there? How big are they? We make perhaps a cumulative value distribution or histogram of the values. Highest and lowest values, some of the outlier values, all kinds of different statistics. We estimate buffer pool misses. How much I/O we're going to have to do to satisfy this query. Are we likely to find something in our buffer? Predicate selectivity using histograms and column cardinality. How many different values are there in this column? And the CPU overhead of doing operators, different operators, join, multiply, compare, etc., to determine an estimated CPU I/O communication cost for doing the query this way, the other way. You try a lot of different ways and pick the cheapest one and do it that way and hope that your estimates have some validity. There's huge errors in the estimates, but in general there's no known heuristics that will do as well as a cost-based query optimizing. Other innovations that were made to make these huge numbers of performance that we got are query rewrite. Some SQL constructs are difficult to execute efficiently if you do them naively. Because in the SQL definition it says, here's what this means. It gives you an algorithm that produces the answer. Well, sometimes that's not an efficient way to do it. Sometimes that's the way you have to do it. So you can be improved by using the semantics of the queries, things like implied predicates. If you have, well, to The answer to this query, A must equal B and B must equal C. Now, that must imply that A equals C. You can use that to make a better query plan. We'll get to that. Nullability, key properties. So they're algebraic expressions, these queries. So we can transform them to equivalent expressions, more efficient, and the improvement can be quite dramatic. Here's one for subqueries. The subquery can be turned into a join. In the SQL, you can say where some column from some table is in this selected set, right? In the values of the C2s from T1. So you think, well, for every occurrence of this thing in the table out here, I'll just whiz through T2 and look for the values. Well, that's Cartesian, that's quadratic in order of magnitude complexity. And here's an example of doing that. Who manages departments with big budgets? So select the employee from employee things. Well, that employee number is the manager of a big budget department. That can be rewritten as select from some distinct managers and make that into a join. So probably the best way to execute this query is as this join, compute the distinct managers with big budgets, and then look up because the employee table is likely to have an employee number index, right? I just look up the employees with those managers of those departments. So you can enforce the distinct on manager number, or you can use early out. That's a trick of when it comes out. If you've got it in, mumble. I don't want to get into that. Too complicated. But it can make a big difference. Here's an example of implied predicates. With these two predicates of this query, which comes from the benchmark, the TPC-8 benchmark, apply these two predicates here. It turns out that you usually have good indexes on that. Turn a 24-second query factor of 10. Became 24 seconds, used to be 280 seconds, until that just subquery to join. And this implied predicate transformation was made. I'm not going to have time for this one. What's this one? Group by pushdown. That's mine. Parallelism. Modern database, commercial database systems are the best parallelized application on the planet, except for certain bomb codes running down the street of Livermore. We have many levels of parallelism. First of all, I/O parallelism. You need many slow disk arms to keep a CPU busy. On the order of 15 or 20 per CPU. You need to strike your data over multiple disks. So if you're reading any large amount of data, you get multiple disk arms working on your behalf. And look for opportunities for sequential data transfer off individual disks, because using disks is sort of the opposite of the drug dealing game. You guys knew that, right? How many know that? Nobody know that? Oh, so you know about drugs. Ah! No, in drugs, the first taste is free, right? You get the first one free, but after that, you pay, right? Disks are exactly the opposite. If you want to read sequentially from a disk, all your costs in doing the read is the first byte. After that, all the bytes are essentially free in terms of in performance terms. So that's why sequential access on disks is so important. It's because the real cost is getting to the first byte. I have done some pretty careful experiments where I used at one point 4K blocks and another point 8K blocks for the same thing. I was unable to measure the cost of the additional 4K coming in each time. Looking pretty careful, right? It was all good to the beginning. CPU parallelism, that is multiple CPUs with a shared coherent memory. Can scale to dozens of processors using dynamic partitioning of the data on that CPU. Efficient shared memory query processing algorithms. And in general, the best way to do this is a parallel version of the best serial plan that we talked about making before with the costs, right? We can sort of mechanically parallelize that and chop up the data and drive it through. That's not been proved formally, but there's a pretty good thesis out of Berkeley that made a really good argument that that was true. There's also cluster parallelism, that here's this multi-CPU thing here running these multiple disks. Through in some kind of interconnect, here we can scale to hundreds of nodes quite easily. And here we must do a static partitioning of the data. We have to divide up the data between the different nodes of the database cluster. And we can use pipeline data transfer between nodes executing in parallel. So I can be computing from my thing and sending you answers that I computed, and you can be combining them with data that you own. And we're all moving data all around the network in general in all directions. And here, unfortunately, we cannot use a parallel version of the best serial plan because communication costs are so sufficiently high that we have to take them explicitly into account and factor that in the different ways of doing joining data basically between nodes, aggregating. If you're aggregating and finding the average, well, you can do part of the work at each node, but somebody's got to do the final average, right, with the partial work. That's all sort of new and different query plans come into play. So, what's going to happen in the road ahead? I'm not doing for time. My clock doesn't seem right. Like what? 20 minutes. Well, I rushed right through this. I'll have to give you another time.
It's not jokes.
So, what's happening in the future? Well, one of the things that database management systems have had to address is that typically we design the things to do certain things offline, like backup, restore, and collecting statistics, and some of the some operations offline, rebalancing in the distributed thing here. If the data got out of balance between the nodes to get it rebalanced, that would be offline. Building indexes used to be offline, reloading them. But in today's world, you can't be offline. There is no Christmas break. We have to figure out how to stay online with the database, 7 by 24, all across the things that can happen. Like you needed to upgrade the database software. You needed to take a database backup. You needed to import a bunch of data from somewhere else. The application that's using the database changed. The operating system you're running on changed. They brought you a new computer, and you have to use it. You got to deal with all this and pretend you're there the whole time. You get maybe 2, 5, 10 seconds. You can sort of miss about that much time before they start getting angry out there on the internet. So availability is tremendously important. And finally, next, what about the dataless database? I hate to admit it, it pains me to tell you that not all the world's data is in a relational database. There's still stuff in files. There's still stuff in, Access, which is not a really database. Spreadsheets have stuff in it. There's pictures, GIF files. That's data. There's the other place, so how can we integrate data from multiple non-relational and relational data sources? It's called federated database. It's beginning to take hold quite a bit. The idea is that you may not own any data, but you know how to pick it off from different people and put it together, even though it comes from different kinds of sources. So you see mashups, for example, of doing that kind of thing today. Familiar with mashups? Take something from this website, something from this website, you combine them and get something useful. Mostly done with graphical, two-dimensional, three-dimensional data, map stuff. Google Maps provides a lot of mashup facilities to its customers. I mentioned early on that the relational data model allows the specification of data constraints and can react to check that changes of the data state obey predicate. Predicate can be fairly complex. If it's too complex, it costs money whenever the data changes to check it. But not only that, you can arrange to, when a predicate becomes true, a condition is violated or something happens to the data, to trigger things, other things. The most common one, which is built into all relational database systems, is the referential integrity constraint. That is, all children must have a parent. That is, if this table has a referential integrity constraint, there must be some column or columns in this table matching columns or columns in another table, the parent table, right? And so that's called referential integrity constraint. We can check that. But if you go off and try to insert a row and there's no parent, it's the matching thing, we can say, sorry, referential integrity violated, we do not allow this change to be made. We can also react to changes in another way. Imagine that the parent is deleted. That the application says the parent, delete this parent row. Well, normally say, well, you can't do that because that would violate the constraint. There would be children without parents. But the relational data standards people and the data modelers said, no, that's not what we want to do at all. We want to say, if the parent is deleted, in great sadness over loss of parent, we must go kill all the children. That's called enforcing referential integrity. So that's an example of data doing something. Something happened to the data, it caused other things to happen. So a lot of this comes from object technology. We think of objects sometimes having triggers on them. We see this in some of the exception managing protocols we see in C++ and in Java. When things happen, actions get taken, but they're sort of non-local. The thing that where the happening happened doesn't really know that the stuff is going on around it. And finally, data mining, that I mentioned right at the beginning. The whole idea of collecting all this data is to somehow profit from it, usually by analysis of the data in some way. Yeah, you can do it to use it to do the business, to send the bills. But the big money that's being made is by analyzing, by understanding your customers better, by serving your students better, by having better tracking, whatever you need to track to keep them serving better. Tests, online tests, I don't know. But anyway, getting value from the data. And a lot of statistical value being derived from the data has margin of error, right? It's hard to see what's really happening because it's not enough data. Because the more data you look at, the further you can drive down the margin of error. So data mining is really the idea of looking at huge amounts of data and trying to find little anomalies that are just above the noise. You might call, I'll steal this phrase from a science fiction writer, distilling facts from the vapors of nuance. Just going out there and saying, oh, we noticed that, people, men, when they go to the store in the evening to buy milk, they oftentimes, to buy diapers, they often end up buying beer. So what we should do is we push in a beer next to diapers. And then we sell more diapers or beer, we're not sure which, but it'd be a good idea. And they can do this by analyzing thousands of cash register receipts, and they've done it. So, an academic inspiration, Ted Todd's seminal paper in 1970. It was developed in research laboratories, most notably the IBM San Jose Research Laboratory and the English Project at the University of California at Berkeley. That coupled with pretty amazing hardware advances. I mean, back in the day, a MIP and a meg was all you could ever ask for, right? A MIP of computer, a megabyte of main memory. Wouldn't it be wonderful to have a megabyte of main memory? It's great. Has really led to the world-changing creation of information value. So this is a real example of the technology that within a span of 20 years became essential to maintaining the cultural, academic, educational, governmental, and commercial activities of our society. It's been a lot of fun watching it happen and contributing in my own minor little ways to this revolution. And so I guess I've left some time for some questions about this or other things.
How were you involved?
I was at the IBM San Jose Research Laboratory at the time System R was being developed in around about 1976. System R was one of the prototype systems that came out, the earliest prototype about the same time as English did, a little bit ahead of it. In fact, it was certainly ahead of Oracle. Larry got the manual and said, okay, I'll look good, I can go do that. He's a smart guy. And was actually the basis for IBM's relational database offerings in later years. So I worked on concurrency control, storage, recovery, query, function dispatch, and query execution, hash joins, intra-query parallelism within one SMP group, and a few other things. Now, I've done a benchmark too. I did a big TPCC benchmark once. The first one to get over 1 million PPMs. So that's been my involvement since about 1976.
Totally unrelated, but you're the first speaker I've ever heard not to have uttered a single during the course of your thing. How did you do that?
Peter Toyce taught me to say mumble instead of mum. So sometimes I'll say mumble when I get confused. And it's important, there's a couple of little tricks people taught me over the years. One of them is never put your hands in your pocket when you're speaking. And keep moving. Don't root yourself to one place. And use your hands. And don't say and.
So what are the future trends? Where is it going from here?
Well, you can almost, in relational databases, there's not a very great deal happening. And of course, in our industry, there's enormous forces building up. So it reminds me, Lord of the Rings or some big things are coming. In relational systems, we'll see a bit more of packaged kind of offerings, more appliance kind of stuff, probably. We'll see a lot more. This is a pretty mature technology. We'll see. There's work being done in queuing in database systems and advancing some of the indexing. Fair amount of fuss going on about column stores that is totally relating to the sequential accesses of this. They're saying, hey, if we're trying to do a scan and filter operation, if we're reading in whole tuples, multi-field tuples, looking at just one, that's bad, we're doing too much reading. Why don't we split the thing vertically and just read in the column? So the column store work, vertical Stonebreaker's work, is looking at trying to exploit exclusively that sequentiality feature of the disk to try to get faster query processing for complex queries, for business analysis queries. That's going on. At the same time, we're seeing these earth-shaking changes in the fabric of our computer universe, that the microprocessor designers have said, we give up. You've seen your fastest microprocessor. We cannot go any faster. We're very sorry. We bring you multi-core in exchange. Well, thanks. I mentioned that database is well-parallelized application, and in fact, practically the only commercial application positioned to exploit a high-degree multi-core machine. First, we run a benchmark on 128 physical core machine, very top-of-the-line stuff. That's 128 cores, right? coherent memory, a terabyte of it. Right? So database can do it. That's the good news. The bad news is, yes, an enormous transaction rate can be sustained and very complex analysis queries over large data sets can be executed here. But in the case of transaction processing, the number of concurrent transactions is really closely tied to the size of your business. You wish you had more transactions, so you would need more parallelism at your website. That when we do 1 million transactions a minute in TPMC, we're doing the equivalent of a web order per person in the United States about every 10 minutes. For a person that has a credit card, sorry. So, I mean, it's not going to be easy to soak up that parallelism. And the truth of the matter is that application programs, all up and down the stack of software, from the word processing programs to the presentation graphics to the application programs that run websites and show you and sell you stuff and check your credit card history and upsell you something else because they said, oh, you bought this book, you're going to be interested in reading that, right? But all these programs have been, for the last 40 years, augmented and augmented with more and more features and functions. About roughly 20% more path length of features and function and Java slowdowns, just inefficiencies, about 20% a year. Good news is that every Christmas the processor designers and fabricators came out and said, it's Christmas time, we give you a 20% CPU performance bonus. We are cranking the clock up another gigahertz, right? And your CPU is going to go 20% faster. This is good because I got 20% more crap code in my application. My clients and customers ain't going to notice a thing. Aha! On we go! 20 years, right? Hey, news bulletin, no bonuses here. You think they stopped putting in the 20%? They won't notice it this year. In about 3 years, they're all going to be saying, wait a second, the CPU is not going any faster. And I'm doing a sequential task. I'm fundamentally, doing this along the sequence. If you go make a web order with your credit card and everything you check out, during checkout, you're going to hit roughly a dozen different processes and threads, possibly on different machines. That's the good news. Bad news is no two at once. So you can either imagine 20% more CRUD going into the application, or you can imagine those machines getting 20% slower per year. And how long do you think it's going to take you to check out in a couple of years? This is a challenge to the software industry, the computer industry, which nobody has a handle on. Everything from functional languages are coming back so we get more automatic parallelism to, oh my God, I better jump off the cliff.
Slightly more topic. You mentioned that the databases, relational databases, were uniquely suited to use the multi-cores, and also that there were a couple of data, particularly files, that were not in database form. Do you see the file structure in computers going from navigational to relational models?
No, I think the file, you mean the file naming hierarchy that we find in most, no, I think that's going to stay. File systems will stay file systems. Data will be continued to be put in files. Databases will be used for more business-oriented and activity-oriented tracking. Files much more static. I think a hierarchically named files are going to continue. There's certain camp that thinks object stores, in which it's a network navigation model, when objects and files will come to be. But all the stuff in document management systems and document stores seems to be preserving the folders and nested folders model.
Any hope for a database backend so find runs a bit faster?
Well, yeah, certainly they're going to be indexing files a lot more aggressively. Many modern file systems, especially in the Linux environment, are already using B trees for their directory hierarchy. And that's a nicely parallelizable and searchable environment. But what we will probably be seeing more of is full text indexing with more semantics. If it's a PDF, they'll figure out where the titles are and they'll index the titles a little differently in the paragraphs and the sentences. So full text indexing of your file contents, your document contents will be much more prevalent. We're seeing it today, of course, to some degree, in the email systems. Notes and Exchange have good searching. And I don't think Exchange has fully inverted indexes yet, and I wouldn't be surprised to see it. So full text inversion will come from files. And more full text inversion facilities for text data and databases. One of the more recent large semantic leaps in relational databases was basically accepting XML as a data type. So you can have an XML column in a table, and you're expecting XML behavior on that column. Like you can search it by its structure, structural predicates, you can search it by the text that's in it. You can operate on it to subset it in various ways using the XML manipulation languages like XQuery and XPath.
So to be able to search inside of Word documents and the like.
If the Word document was inserted into a field well, Word's not XML yet. But there will be a lot more text indexing, I think. And it will be on your laptop. So all files will be content searchable. And the real question is, how aggressive are we going to be on analyzing the semantics of the file content, analyzing and understanding the semantics of the file content, so-called annotators or text miners. And we're seeing some of that people are just going through text files and finding names, addresses, phone numbers, and classifying them as part of the indexing of those objects.
Well,
Am I getting the hook here?
well, you're getting the. But if you want to finish on a entertaining joke, you can do that.
Well, you have to have the question that triggers such a joke. Rather big no jokes or questions that.
Do you have any advice for somebody who's basically managing a very large, ever-growing document database?
Well, there's so many products out there, they're not cheap, that can help with that. Documents in all different formats, I presume, and stuff like that. There are, like I say, products out there documenting file manager from IBM that can help with that. Pretty good stuff in some of the mailing systems. Notes has a bunch of database stuff. They do pretty good indexing of those sorts of things. Text indexing, not as good, I don't want to say good. It'll do text conversions, but not very good ones. That's sort of the state of the art there. And there are products that deal with that. Where large is expected to be in the thousands and millions.
Well, thanks very much.